For years, the path to smarter AI seemed pretty simple. Just go bigger. But what if that's only half the story? Today, we're digging into a really fundamental question. To build truly intelligent systems, do we just need bigger AI brains, or do we need to teach them how to think better? To get our heads around this, let's imagine we're all studying for a massive exam.
So picture it. You're prepping for that huge exam. You've got two basic strategies. The bigger brains approach is to study for 1,000 hours, cramming every single fact you can find into your head. The better thinking approach, on the other hand, is to use your 1 hour of test time perfectly, thinking through each problem from every possible angle. For a long, long time, AI development has been all about that first strategy, just more and more studying.
Right, so this bigger brains philosophy, it's not just a hunch. It's actually guided by something researchers call training scaling laws. And for years, this has been the main playbook in AI, all based on one powerful idea. The rule was basically, if you want a more capable model, you just scale everything up, feed it more data, build it with more parameters, and throw more computing power at it. And hey, this gave us incredible progress. It's kind of like building a bigger and bigger library. But at some point, you don't just need more books. You need a brilliant librarian who actually knows how to find the right information and connect the dots.
And that, right there, brings us to this new frontier. Instead of just focusing on the studying phase, what if we zeroed in on the test-taking phase? This is the whole idea behind scaling inference compute. That's the work an AI does the moment you ask it a question. It's not about just knowing more. It's about thinking harder.
So how in the world do you make an AI think harder? Well, let's look at one of the first and, frankly, simplest methods, which happens to have a pretty memorable name. You gotta love this. Researchers from Stanford, Oxford, and Google DeepMind literally called their paper large language monkeys. It's a fantastic nod to that old thought experiment, the infinite monkey theorem. The idea that if a monkey just types randomly for long enough, it will eventually type out all of Shakespeare. So the AI version of this is basically a simple brute force strategy. First, you get the model to generate hundreds, maybe even thousands of different answers to a single problem. Then you use a second program called an automatic verifier to sift through that mountain of answers to find the one that's actually right. So what exactly is this verifier? Well, for some tasks, like writing computer code, is super straightforward. If the AI writes the piece of code, the verifier can just be the unit tests. It runs the code and checks, does it work? Does it produce the right output? It's a clean, automatic yes or no check. Now, this brute force method does something pretty amazing. It dramatically increases what researchers call coverage. Coverage is just the chance that the correct solution exists somewhere in that huge pile of answers, even if 999 of them are junk. If just one is right, you've got coverage. And you can see just how well it works. On a really tough software engineering test, one model, DeepSeek Coder, only solved about 16% of the problems on its first try. But when researchers had it generate 250 different samples, whoa, its success rate jumped all the way to 56%, blowing past the old record. Turns out, more monkeys really do give you a better shot at Shakespeare. But, and this is a huge but, there's a massive catch. Because having the right answer somewhere in the pile is one thing. Actually finding it is a completely different and much, much harder problem. As the researchers put it, the challenge becomes finding the needle in the haystack. The more answers you generate, the bigger your haystack gets, which makes it even harder for your verifier to pinpoint that one correct answer hiding in a sea of almost right attempts. And on math word problems, this issue becomes crystal clear. When generating 100 samples, the correct answer was in there almost 83% of the time. At 10,000 samples, that potential coverage shot up to over 98%. But look at the actual score. It barely moved. The verifier just could not find those needles. This happens because there's this massive gap between different types of problems. It's easy to verify code or a formal math proof. They either work or they don't. But how do you automatically verify the quality of the reasoning in a math problem or the creativity in an essay? Judging quality is just so much harder for an AI to do. So this whole verifier bottleneck proves that more brute force isn't always the answer. And this brings us to a much more sophisticated approach, pioneered in a new paper from Google DeepMind. The researchers at DeepMind asked a different question. Instead of just generating more and more random answers, what if the model could intelligently adapt its problem-solving strategy? Just like a smart human test taker would.
They call this idea compute optimal scaling, and it's based on a simple truth we all know. Not all questions are created equal. Some are easy and just need a little polish. Others are incredibly hard and require a complete rethink from the ground up. The key is to use the right amount of thinking for the right kind of problem. A smart test taker knows this instinctively. For a really hard problem, you brainstorm. You generate lots of different ideas all at once, in parallel. But for an easier problem, where your first draft is pretty good, you don't start over, you edit and revise it, step by step. This new approach basically teaches the AI to do the same thing. And the optimal strategy they came up with is beautifully simple. The AI first takes a guess at how difficult a question is. If it thinks it's easy, it allocates its thinking budget to refining and improving its first answer. But if it thinks it's hard, it uses that same budget to explore many different starting points. It adapts. And the results are remarkable. This adaptive compute optimal strategy can get better results than the old brute force best of n method while using 4 times less computational power. It's not just about thinking harder, it's about thinking smarter. So what does this all mean for the future of AI? Where do we go from here now that we have these two competing philosophies? What we're really witnessing here is the emergence of a whole new set of rules. For years, we've been guided by training scaling laws, where bigger is better. Now we have inference scaling laws, which are all about smarter thinking when it's time to perform. It feels like a shift from just building bigger brains to building better thinkers. And the direct comparison is just stunning. For certain problems, giving a smaller model more time to think intelligently is actually more effective than just using a massive model that's 14 times its size. That really suggests that raw scale isn't the only path forward. This leaves us with a fascinating question for the future of AI. For a long time, the race was all about who could build the biggest model. But this new research suggests the next great leap might not come from building ever larger digital brains, but from finally teaching them how to truly think.